Hello and good evening, everyone. My name is Mohammed, and I am part of NeuroTX Aachen. Today, I would like to welcome you to our first event that we do, and also to tell you more about the word of neurotechnology. So, the momentum, and what do I mean by it? So, when I talk about the momentum in the 21st century, what I really mean is actually the technological momentum. This metaphor was proposed by a historian of technology named Thomas Hughes in order to describe the way by which technological systems are developed and gain stability. So I hope already most of you know that in physics, momentum is the product of the mass of an object with its speed in a specific direction. So the more momentum an object has, the more difficult it is to slow it down and to change its course. Now, this is very relevant to our topic for today, namely neurotechnology, since as a new emerging field, we are now at an interesting point in history in which we have to decide in which direction we are heading. So what are the goals that we aim to achieve from such technologies, and what are the possible negative implications and how we can avoid them? These are all very important questions that we have to find an answer to. However, the main question of today, which I would like first to answer, is what is actually neurotechnology? So neurotechnology is the assembly of methods and instruments that enable a direct connection of a technical component with the nervous system. So this assembly can be either to record signals from the brain. So this can be electrical, magnetic, or metabolic signals. Also, this can be even extended by translating these signals into control command of a digital device, such as robots, drone, or computers. In addition, we can go even further and try to manipulate the brain activity by applying an electrical or an optical stimulation. But yeah, what are these methods and instruments that I speak of? And basically, in neurotechnology and also similarly BCI, so brain-computer interface, they are, one can say, divided into two main categories. So the first, which is the non-invasive neurotechnology. These are the simply any type of sensors that can be placed on the surface of the head and can then pick up activity generated by the brain. So these methods are termed non-invasive as the electrode themselves do not penetrate the head or the body. So the most common brain activity recording techniques that are used include EEG, so electroencephalography, that record the electrical activity of the brain when a group of neurons fire together. Also, similarly, the MEG, so magnetic encephalography, it measures the magnetic field produced by this electrical activity of the brain. In addition, we have also other tools such as the FNIRS spectroscopy. So here the surface layers of the brain, of the cortex, are assessed, and then blood oxygenation is measured, and by this method, one indirectly can measure the brain activity. On the other hand, we have definitely then the the invasive approaches, such as the electrocorticography. So here a piece of bone is removed, and then the device is placed directly on the exposed surface of the brain to record the electrical activity from the cerebral cortex. So also we have the single or multi-unit recording using microelectrodes. So we have here the famous Utah array. Don't be scared by the look of it. It doesn't. So basically, it is implanted in the brain, but it's not so big. So it's around 2 millimeters. And this has already set an important standard in such implants. But also, maybe most of you have heard about the latest news that, for example, Neuralink has produced a new implant that has up to 3,000 electrodes. So the old standard ones, the Utah array, have 96, but with Neuralink, they have up to 3,000, and they call it the Link. And this device can be inductively charged. So first, this device is fully implanted in the body. There is no outside part. And then this can be inductively charged. And this is done using a surgical robot that can do this surgery within 1 hour. So Neuralink implanted these devices in several pigs and were able to decode joint angles based on the neural activity. However, it is important to mention, until now, only the Utah array have the FDA approval. So seeing the two previous slides, one can already tell there are two, or not only two, but major advantages and disadvantages in both approaches. So to start with the advantages of the non-invasive one as the one that we see here down, so here MEG and here EEG, these systems are obviously quite safe. So there is no need for surgery. They can be easily removed. And when the patient doesn't want to continue with the measurement, they can just simply remove it. And you don't have to set a specific lifetime since they are only on the outside. However, the major disadvantage is the quality of the signal. So the type of signal that these measurements do record is not as good as the other invasive ones. Also, and in addition, sorry, you will need to use these, what you see here in the picture, the cap. And in the case of EEG, you will have to add gel to improve the conduction. And the application that one can use with BCI is some sort of limited because of the quality of the signal. However, on the other hand, the invasive neurotechnology, and here come the major advantage, which is the very high signal to noise ratio. Also, one can say that they are more practical since once they are implanted, you would not need any preparation time, and they are already calibrated to the person who has the implant. However, the major disadvantage here that there is a higher risk of getting infections and bleeding. Also, any type of implant, so once these devices are implanted, they will need surgery. If they go wrong, if something gets broken, they need to be removed directly. And also, in general, removing anything will need a surgery. And there is no certification until now that for permanent use. So these devices are not meant to be used forever. They are also only allowed to be used inside of a lab environment. So once they are even implanted, you cannot go outside of the lab without with these implants. And here in this, on the side, on the left, we see where are these different measurement modalities are sensitive to the brain. So on the EEG, we can already see that it's quite far, and there are several layers that can distort the signal. However, on down here, you see them that, for example, in the Utah array, they are exactly near the source. Where can they measure single unit activity? Obviously, there are more issues to discuss, but the most important takeaway is that the non-invasive systems have to increase their signal quality, whereas the invasive approaches have to improve the biocompatibility of the material implanted. And the way also these implants are implanted. Next slide. So a somewhat more futuristic variant of neurotechnology is the use of innovative methods from optogenetics. So here the nerve cells are made photosensitive by inserting artificial light receptor into their membrane. So this is very similar to how nerve cells work in the retina. So there are also nerve cells, they are responsive to light. However, originally, these cells are not responsive to light, but one can make them responsive by changing their genetic code. And by just shedding light on them, you can either deactivate them or activate them, depending on which wavelengths you are using. So what is the color of the light? And you can see from this picture here that how when you're using electrical stimulation, you are not very accurate in stimulating one neuron, or you might even activate the 100 around that neuron that you want to activate. Whereas in optogenetics, you are very sure about your excitation place, and also the same in inhibition. So this technique has the advantage of being very specific in the place of activation or inhibition. However, the major disadvantage here, this will need genetically engineering manipulation that make these nerve cells responsive to light, and this means that you would require modification of the genetic information, and this is carried out by viruses, manipulated viruses. So what are the possible applications where we can apply neurotechnology? And an important place where we can use such technologies is obviously the medical field. So before getting started with the example and the different type of BCI, it is very important to say that every 40 seconds, someone has a stroke in the US, and stroke is the leading cause for long-term motor deficit and motor reduction. So in the world of BCI in neurotech, there are two strategies to improve the quality of life among stroke patients. The first, named assisted BCI, so the one that we see on the left, Here, the BCI system aims to bypass the damage of the neural pathway by providing a different pathway, so another pathway. So what happened here is that you measure the signal directly from the source and try to translate these signals to command control of an exoskeleton. So this is called here an exoskeleton that can be then controlled by these signals that measures with the EEG. And you can see that this stroke patient who is not able to open his left arm, he can then open and close his right arm and then also, try to grab things with it. Also, the other type of BCI is then, or the second strategy is called rehabilitative BCI. So here is a different approach that uses the neuroplasticity of the brain that Mariana already spoke about before. But to repeat, what is actually neuroplasticity is the ability of the brain to reorganize itself throughout life. So when there's an area that's in the brain that is responsible for controlling a certain function, for example, moving the arm, and this area is damaged by the stroke, one can use neuroplasticity to move this function to a different area. However, this is done by telling the stroke patient that he or she should try to imagine a certain movement, but it's very hard for the patient to know if they are doing the task in the right way. So what happened is that the BCI system recognized this pattern of activity, the brain activity, and try to show it to the patient as visual feedback, so the patient would know that they are doing or performing the task correctly. The invasive example of such technology is also the famous cochlear implant. So this is a small device that has two parts. One is on the outside that you can see here, upper the ear. And this works as a microphone that measures, so it takes sounds from the environment and transform it into electrical signal. And this then sent to the internal part. And the internal part then will have a wire with electrodes on it. This wire will go inside until the inner ear, so until the cochlea, where there will be the cochlear nerve. And these electrodes on the wire will then stimulate that nerve based on the signal that it will get from the outside part. And then this nerve will send the information to the brain, and by it will produce the hearing sensation. Also, a similar approach is, people are trying to do it with vision. So there is the cortical vision prosthesis, which is still in development. So people are still researching on it, and until now there is no functional example of it. However, it will work with more or less similar principle by taking the information from an outside camera, translating these information into an electrical signal that will be sent through this implant to the visual cortex, and by it restore the vision of blind patients. The other important application of neurotechnology is also obviously in research and specifically in neuroscience. There are many questions that until now we don't know the answer for it. For example, what are the causes for neurological disorders such as Parkinson or Alzheimer? How are our movements so fine and controlled, and what are the basis of decision making? Many questions are yet to be answered. However, with the aid of neurotechnology, such as here what you see optogenetics, it has become much easier. For example, it is not only possible to measure the activity, but also to see where the activity is coming from. And also we can, with this technology, for example, in live calcium imaging, we can also see what the neuron is receiving from an input. So what you see here, that this is a single neuron receiving input on its dendrite from different parts. And we can understand and try to see what this neuron is trying to computing, and then apply it to computers who try or want to replicate how the brain functions.